frontier using Excel. I'm gonna copy down the equations also. Now what we'll try to construct a efficient frontier using CLA algorithms. We'll start with the date, okay, and I'm taking a two stock approach, and I'll directly take the stock prices, stock returns, return 1 and return 2 also. So what we'll do, first of all, we'll get the data, and I'm going for the yearly data. You can take the monthly data and just scroll around till we've got sufficient number of entries, okay, and I'll use the rand between command to get myself some data, okay. So you have studied that thing over here in your class also, okay, how to get this data, and then I'll copy that thing over here and then paste special using values that the values get fixed. Okay, now this is the data I've got, alhamdulillah. Now these are the returns, and these are the what I'll be doing. I'll be going for the average returns, the proxy average returns, return for R1, then R2, then I'll get variance of 1, variance of 2, and standard deviation of 1, standard deviation of 2, just for the sake of that I get all the values. I'll take the average of the first series. This is the average of the first, and average of the second series will be like this. I'm building this thing like this because I'm going for the row matrices, because I'll apply the matrix operations, and matrix operations make the thing simpler for us. So this is the variance also, and this is the variance of the second. Then I get the square root of the variance is the standard deviation, and easily copied. Check it out. I've got that thing. Okay, now I've got this thing. Now I'll go for the weights 1, weight of second, and this is equivalent to 0. Equivalent to 0 for the time being. And the total should be how much? If you remember, it should be the sum of these two, and eventually it should be equal to 1. Because the weights are 0, then the sum is also 0, but it should be 1 over here. Now what we do, first of all, we will calculate the portfolio risk, then the portfolio return, and we'll get some lambda values. Lambda values can be inserted over here. You can get the symbol over here. The lambda symbol is here. Okay. So lambda values and I can take the lambda values that were given over here. Like these are the values I've got. So I can go for these values. The values are big enough, so I'll write it myself. 0.001, 0.005, 0.05, 0.1, 0.25, 0.5, 0.75, 1, 1.5, and 2. These are the arbitrary values. It's not necessarily you can take these values. You can take other values also, but for a give just for easy sake. Oh, sorry. One, 1.5 into 1.5 into and let me delete and shift the cell up, and this thing got deleted. I'll put it back again. Okay, oh, it's up over there, sorry. So these are the lambda values. These are arbitrary values. We can change accordingly from the data set also. And now we've got the row matrix over here, for the weights and the standard deviation. If you remember the portfolio risk, if I say portfolio risk is equivalent to if you remember it is the transpose of x and multiplying by covariance matrix into the weight matrix. That means first of all you will multiply the covariance matrix by the weights and then multiply the product by the transpose, so you get the portfolio risk. You get this figure, and in order to calculate the portfolio return, this is you calculate transpose of weight into your returns, average return. These are your average returns. Okay, why this thing is like this? Because this is a 2 by 1 matrix and weight is a 2 by 1 matrix. 2 by 1 is, if I take the transpose, it's become 1 into 2. The matrix becomes 1 into 2 and multiply by this matrix, that is 2 into 1. When the inner product is the same, then what happens? The result is you get a 1 by 1 matrix. Okay, this is why we have done this thing. Why I've taken the transpose? Because it was a row matrix over A 2 by 1 and a row matrix over A 2 by 1. We took the transpose of the weight matrix, that it became 1 by 2 and multiply by 2 by 1, we get a 1 by 1. And what is happening over here? Again, I'll copy that thing down, put it a bit low. Okay, what happened over here? Okay, the covariance is a 2 by 2 matrix, and this is a 2 by 1 matrix. The weight is 2 by 1 matrix. When the inner product is the same, what you get, eventually get 2 by 1 matrix. Okay, good enough. Now again, now you have to multiply with the x, and x the weight, that is 2 by 1. If you take the transpose, you get 1 into 2 matrix. Now the inner product is the same. The inner product is the same. Okay, inner product is the same. So eventually you get 1 into 1 matrix, that is a single figure over A. So this is how do it. What you have to do also, you have to do it manually also. Prove that thing. Okay, if you go with this formula, this is the formula for portfolio return. This can be written in this form also. It does not make any difference. What you can do is you can this formula and this formula and this formula are the same. Transpose of weight into covariance, the product of covariance into the weights. Now, this formula, this thing is the same. What you do, you multiply yourself manually, eventually get this formula. Okay, this is not my work. Eventually, this is a small assignment for you also. So this is how we can run the matrix operation. So in order to calculate the portfolio return, we had this formula, but instead of using this formula, we used the matrix operation. and for this return also we use the matrix operation, and the lambda values will be put it over here, and build we build a z function over here, and the z function is equivalent to the transpose. Now what I forgot, that we don't have a covariance matrix over here. So first of all we have to go for the covariance matrix. Go to data and data analysis and covariance, and their covariance is there. The output is, the input is, I go for the input over here, and the output is over. Okay, I'll put it over here. Okay, and include. So this is the covariance matrix, but I don't have the diagonal entities, so I can copy over here and space special transpose like this. I get these values, then again copy over here and put it back over here, skipping blanks. So I get the cross diagonal entries over here easily. This is a 2 asset case, is easy, but we've got 100 asset case, so you can't copy each and every value, the cross diagonal entry. This is a small command you can follow. Okay, now we've got the covariance matrix, we've got the weight matrix, we've got the return matrix, we've got all the inputs we have needed are there. There might be some confusion. If you remember the covariance variance matrix, this is the variance and this is the variance over here, but these values are different. Now what is happening, this, when you go for the covariance command, it goes for the variance of the population, and over here you have calculated the variance of the sample. So in order to go for the population, you put a p over there, the value becomes equal. Again a p over here, the value becomes equal. Now the values are equal. Why? Because when you build the covariance matrix using this command over here in data analysis, the covariance variance matrix, the variance is always calculated as a sample. But when you directly calculate using var function, not a variance function, so this says that this is the variance of the sample, but when you put a p over there, it becomes the variance of the. So either way, if the data is big enough that you've got more than 30 entries, normally in finance we take up to 4 to 5 years data, monthly data, that means 48 or 60 entries, then they tend to converge together. They tend to become similar, not identical but similar. So either way, if you want to use this or that, it's okay, because when you are going for this formula, you'll be using this, and when you're going for the matrix operation, you'll be using the variance covariance matrix. So I put both of them together. We can build the efficient frontier. We can manually write this formula in the z function, and or we can go for this matrix operation. But when we write this manually, if you've got 100 asset case, to write 100 for 100 asset case, you have to write 100 variances, and the covariances n into n minus 1, that is 100 into 99, that is 9,900 covariances you have to write. Then it's a very difficult case. Then in that case, transpose this matrix operation becomes very similar, very easy. Anyhow, this is how you start, and I start with the first of all, I go for the portfolio risk function. And that will be equal to MMULT, that is matrix multiplication transpose. Spelling mistake. Transpose of my matrix into comma the multiplying covariance matrix by the weight matrix. Okay, if you want to block it, you have to write Control Shift and Enter. Okay, you'll get these brackets. These brackets only come when you write over here, when you click over here, that is Control Shift and Enter together. These are the three. You have to put it like this, then you'll get this brackets, and now it's complete. If there was an error, then the figure won't be there. Now you have to have portfolio return, and the portfolio return is to be calculated directly. MMULT is, if you remember, is transpose of weights, okay, multiplying by the return. Okay, so put the bracket, Control Shift and Enter. Okay, now I've got these value also. Now I'll go for the Z function, and Z function is equal to portfolio risk minus lambda value, I'll put a bracket also over here, into steric the portfolio return. Okay, this is the function. Now I've created all the functions that I needed. Now I'll go for the optimization equation only. So I'll put a try to color this thing to make myself remember this is the optimization function, and these are the important functions over here that I'll be using. I'll put getting it yellow because I have to remember which fun, and these are the lambda values I'll be taking. Okay, so what you'll do, you go to the data and you'll go for the solver. You've got the solver function. First of all, you've got to select the target cell. The target cell is Z. You have to put 0. Now you have to maximize or minimize. Yes, we have to minimize. And what are the cells we will be changing? We will be changing the weight cells. And what are the conditions I want? I'll say that all weight should be equivalent to 1. Okay. What does say that this cell is equivalent? Sorry, it says this cell is equivalent to 1. F13 is equivalent to 1. Why? Because all weights are equivalent to 1. Now, if I want to go for the short cells as not allowed, I can put this value over here that it should be equivalent or greater than 0. Actually it is greater than 0, but Excel does not have this option, so we put the sign like this, equivalent or greater than, the sign like this, equivalent or greater than. So we don't need it for the time being, so we are not going for any other constraint. This is the only constraint we've got. So what we do, we solve it, and what does it say? It says solver found a solution, all constraints and optimality conditions are satisfied. Alhamdulillah, everything is. So these are the portfolio risk, this is the return, and this is the Z value. Actually we don't want the Z value, but still I'll copy that thing over here and copy values. These are the values, and if necessary I can put the X values if I need the X values also. Sometimes you want to see what the weights are coming like that, and all weights are equivalent to 1. The condition has been met, and the portfolio risk is 19. That is the variance. And the return is 17. Okay, good enough. And the lambda value is how much? I'll put that thing over here also. The lambda value was, when the lambda value was this before. Now what I do, now I change. So what was the lambda value over here was, I'll change this value and I'll give another value also. That is this one. Okay, I've changed it, and now I'll solve it for the second lambda value, and I got a solution, and this is the solution I got. So what I do, I paste this thing over here again, and the weights also, weights are not changing so much because the lambda value is not changing, is not changing that much. Okay, now again I'll change the value to 0.5 and then go for the solution, and now if you observe, the values are changing again. Okay, the weights have changed but not significantly, and now I'll go for the larger values. I'll take the value of 0.75 and then go for the solver solution, and it gave me a solution. Okay, good enough. The value changed, but it's not changing that much. The value is 0.75 because these are arbitrary values. The weights have changed significantly. Now I change again. I'll give a value of 2. So now here the change is quite significant. So that means if you take larger values, what will happen? And this value was, I think so, 2. So why not take 4 then? Okay, now I'll solve for another. So what happened? Now the solution came up when I'm taking larger values, it is giving me a good solution. Okay, with weights also. And over here we've got 4. So we can take arbitrary values. I'll try it for 8 also. Perhaps I might get a good answer for it also. Okay, and then we keep on repeating. These are the algorithms that we, and the answer is, let me check also what is the range. The range of return is sometimes because short sales were allowed. This is a very high value. Why not I take a lesser value? I take 4, I take 6. Okay, this is not a good value that I'm getting. Okay, it might be tedious, but still, and I can take, if you go for a trend, when you are increasing this lambda values, the change is there, and the change is more conspicuous in this part. Okay, that means you have to take some values in between also, like insert and write. Why not I take the value of 1.5. Okay, 1. I'll take a value of 1 also. Insert good enough. 1. You keep on doing and keep on. You'll do it so many times that you'll remember this was something. Okay. uh, Actually, the computer does it for you. It does it in a split second. But in Excel, we have to learn how we are following this thing. No? And the weights over here, you can make a observation also. 1.5 and 1.75. The last is 1.75. I'm taking from here. Okay. All constraints met. Good. So we've got a lot of figures now. So this is the portfolio. Sorry, this is the return we need. Portfolio return and portfolio standard deviation is important. So I take the square root of this. So this is the square root, and these two values are important for me to build the efficient frontier, if you remember. And I'll shade them by with the lighter color. Pakistan is green, we get a green. Okay. So these are the values. Now what you go to this insert scatter, and I select this one. Now this is empty. Select data, add data, efficient frontier. What is X? X is the standard deviation, not variance. Okay. Or what is Y? Y is your missed something out. So add efficient frontier. X is your standard deviation, Y is your return, and you get an efficient frontier. Okay. These are the. Now what is happening? We are not getting these points, the lower points. We are not getting the lower points. We are getting the higher points. Okay. Why we are getting the higher points? Why we are not getting the inefficient points? We are only getting the efficient point because of the lambda. Lambda is the slope of the line that is taken as positive. If you take the negative, we might have got these values over here, or the values over here, but you are not getting those values. And if you try to go more, the last value was taken as 8. I can take more values, construct 8, 10, 12, 13. So this would go up to like this, this point over here. No? So you can do that thing also, but take that thing account. The one thing into account when you move up, because short sales are allowed, you'll get negative weights also. So you don't have to get confused. Otherwise, you can put the condition that short sales are not allowed. In order to do that thing, we put a condition over here. We add a constraint. This it should be equivalent to or equal to 0, and another constraint that this weight over here is equivalent to over 0. Okay. So I've closed this function. So I'll again open the question. So these are the two constraints. That means this function and this, sorry, this weight and this weight is more than 0. So these two are more than 0. We have to do this thing. We can put this, and this means that short sales are not allowed. When short sales are not allowed, now what you do, for example, if you want to optimize, first of all I have to optimize. I'll put a value of, for example, 8 over here. I'll put the value of 8, 6, okay, 6, okay. Okay, now I'll optimize. Okay, what happened? I got the same answer, but when you go for, if you remember, if you go for 8 or 8 value, I was getting a negative value. Okay, hold on, I'll change and I'll give this value. And now what I'll do, the weights came like this. I'll copy and the answer is like this. Okay, I'll put the answer over here. Okay, this is the answer I got with short sales not allowed and with the weights in it. Okay, in research you have to do a lot of comparison. Now what I do, I remove the short sales, delete. Short sales not allowed has been removed. Now short sales are allowed. Now I'll solve them and the answer is there. And what happened, if you copy that thing over here, the values here, okay, and these are the weights you are getting. Okay, the weights are there. So now when you make a comparison, it does, when short sales were not allowed, what will happen in order to optimize and we want to get a feasible solution, it gave us that in asset A we should not invest and we should invest all the thing in asset B. But when short sales are allowed, it says, what does it says? We go for borrowing and then we go for lending. The total weight is this. We go for borrowing, this is borrowing, and this is basically lending. Okay, if I'm not mistaken. And it gave us a solution also. Oh, sorry. Yes, okay. It gave us a solution also. This was a solution, this was the risk, and this is the return. And over here is the risk and the return. Now see, the return over is 31% and the over 29%. The variance is 76 and 57. There is a difference. Now short sales, what happens? When you go move up, the short sales allowed and not allowed become prominent. Over here till now, the short sales allowed and not allowed are more or less their answer is the same. But when we go move up, so the short sales will come like this, and the short sales not allowed will be having a lower value as compared to short sales not short sales allowed. Okay, sorry, my mistake. It's if I want to make a efficient frontier using smart phase, so it would be short sales it's short sales allowed, short sales not allowed, and this is, it would be, oh my mistake, and short sales, this is short sales not allowed. So now this is the difference. The lower curve is short sales not allowed, and the upper curve is short sales allowed. So what happens when we go for the short sales allowed? It gives us a better solution as compared to short sales not allowed, because when we draw line, perpendicular line from your uh, from your risk till here, what is happened? For the same level of risk, it is giving us more return. It is giving us more return as compared to this point. So we are getting more return for the same for the same level of risk. So short sales are allowed, are basically superior, is a better give us a better efficient frontier as compared to the short sales not allowed. Jazakallah khair. This is all we have to do. You can take, just remember, you have to take different values, arbitrary values. It is not necessarily you take these values, you can change, you can go for your own values. Okay, Jazakumullah khair.